Yes. Okay. So let us start. Let's look at yesterday's lecture quickly. That was December 20, and we talked of automorphisms of an object in any given category. The category we took was metric spaces with distance preserving maps, and we took our metric space to be R with usual metric, and we found that the distance preserving bijections from R to itself are translations or flips, multiplication by plus minus 1, or their composites. And we also talked of automorphism groups in various categories. So for a finite set with n elements, the automorphism group is a permutation group on n letters 1 to n. The automorphism group of the real line with this constant metric, distance varying automorphisms, we found the automorphism x goes to lambda x plus c can be written as this matrix, and then the composite of automorphisms is multiplication by matrix. So this is a certain matrix group. I gave it as an exercise to you that for the ring R of real numbers, the only ring automorphism is the identity map. I left it as an exercise to you to determine what is the permutation, what are the automorphisms, what is the automorphism group of the permutation group S3. We are going to do it. Then we started again revising our Hausdorffness, and we wrote a number of equivalent conditions and checked their equivalent. So Hausdorffness in terms of disjoint neighborhoods or pairs of points is the same as diagonal being closed, is the same as for every space Y in continuous map, the graph is closed. Same as the equalizer being closed in Y for any two maps. F and G equalizer is where the two maps coincide. And all these equivalences we proved simply by using arrows and universal properties and not going to neighborhoods. For a topological group, we had various additional formulations for Hausdorffness. One was the original disjoint neighborhood, that is the same as every point is closed. Same as there exists a point which is closed by homogeneity, same as identity is closed. Then that gave back E is closed via the map G cross G to G, G times H goes to GH inverse. So from that diagonal was closed being inverse image of E. Then every discrete subgroup of H of G is closed in G if G is Hausdorff, that we proved in the last lecture of the previous week. But that in turn implies there exists some discrete topological group which is closed, because after all I can take identity. And then that means E is closed and you are back to Hausdorffness. Then we introduce the notion of connectedness through the notion of a disconnection. A disconnection of a topological space X is a pair of open subsets, both non-empty, disjoint, whose union is everything. Connected if there is no disconnection. Then we said that if I have continuous surjection and if X is connected, then Y is connected. We gave a proof. Then I told you about this most important theorem in elementary mathematics first year, that the interval 0 is connected, and I told you the proof. The proof depends on the existence of supremum or infimum for bounded sets, and that or the same as completeness. Okay. In GL and R connected, we'll address it later. Then we talked of path connectedness. Because the interval is connected, we can use it as our instrument to probe the connectedness of other spaces. That gives a new version of connectedness, a stronger one called path connected. Which means given any 2 points, they can be joined by continuous path. A continuous path is a continuous map from the interval into the space. So we also gave a proof here that path connected implies connected, but I told you that the converse is false, and I asked you for examples. Now we have to talk of connected components of topological space, locally connected space, locally connected space, path components of space, all such things we will do. But then we ended with the exercise that if there is a topological group and if there is a normal subgroup, give G mod H the quotient topology, then G mod H is Hausdorff and AFS is closed in G. And you are supposed to do it without using any neighborhood arguments, but through diagonal, etc. Okay, that was the previous lecture. So, as usual, question. Okay, any questions? I fulfill the statutory requirement, as if there is such a statute, that I give you a chance to ask questions. So if you are there and listening and awake and have questions, take this opportunity. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. There are no questions. Great. Let's go. So we come to today's material, and let's recall the definition of connected or disconnected in terms of open sets. And so that definition said that this was X, and there are going to be two subsets. One is U and the other subset is V. And both are non-empty. U not equal to empty, V not equal to empty, X, U intersection V equal to empty, and X is U in V. This means disconnected. Such a pair U comma V is a disconnection of X. Connected means no disconnection exists. Okay. Now I am saying that equivalently X is disconnected if and only if it admits a surjective map to a discrete two-point space. Actually, this is the set which we had defined as 2. I want to show you the definition of 2 in my first lecture. Here it is. AFS Topology lectures week 1. This is the first lecture. It began by saying set theory, and it told you everything is made of sets. And then we looked at how natural numbers are made of sets, and we defined n to be the natural number whose members are 0 up to n minus 1. These are exactly n elements. That's why it's useful as a model for n. And so 2 was 0 and 1. And so this set you can call 2. So there should be a surjection, and give it the discrete topology, there should be a surjection f from X into 2. How do you get this surjection? If it is disconnected, so one way, given a disconnection uv of X, define f on u to be equal to 1 and f on v or 0. First element was 0. F on v equal to 1. This is non-empty, so I am sending all of it to 0. All those points I am sending to 0. The image of this is 0. If you want, you can write a little curly thing here. Okay. And so that's a surjection. Why is it continuous? Because inverse image of 0 is u, which is open. Inverse image of 1 is v, which is open. And 0 and 1 are both open here, because this is discrete topology. So I produce this. Conversely, given f such and f, put u equal to f inverse 0 and v equal to f inverse 1. Why are these disjoint? Because how can the image be both 0 and 1? So of course they. Why are they non-empty? Yeah, somebody wants to answer? Yeah, you are right. Because it is surjective. Yes, yes. Because it is surjective, this is non-empty. There is indeed something which goes to 0, and there is indeed something which goes to 1 because it is surjective. Good. I notice a dramatic improvement in the rate of answering questions of you guys. So very good. Keep that up. Now, so examples. Now you are supposed to answer whether it is connected or not. So example, is R connected?
Yes, sir.
Yes, and we proved it last time. Interval is connected, etc. Is R star, that is R minus 0, connected?
No, sir.
And why not?
Sir, we get two open disconnected sets and the positive real numbers and the negative real numbers. I mean, except 0.
Wonderful. So this is connected. And now he has given an answer in terms of disconnection. Can you give an easy answer in terms of such a map? Remember, maps are always more useful than dealing with points and sets and whatnot. Yeah, so define fx to be equal to
X by mod X.
absolutely x by mod x. So this gives a surjection from here into which discrete set? 1 and minus 1. Okay?
Yes.
And this is surjective continuous. Why? Because mod x is continuous. So 1 upon mod x is continuous because the map from R to R sending x to 1 upon x is continuous on when you are on the subset R star. And then this is the product, so that is continuous. So this is continuous, etc. So you use all the previous things. Okay. Now how about rational numbers? Is this connected?
Sir, I guess disconnected.
Why? Give
Sir,
any answer. Disconnection, map, anything. Give.
sir, root 2 is irrational. It's not in Q.
Wonderful.
So we can separate by rationals which are greater than root 2 and which are
Wonderful.
smaller than root 2. So yeah.
Wonderful. Yes. So let U equal to set of all x belonging to Q such that x square is less than 2. And V equal to set of all x belonging to Q such that x square is greater than 2. U union V equal to Q as root 2 is irrational. There is nothing whose square is equal to 2. So either it is less than 2 or greater than 2. So, and both of these are open. Why? Because x times x multiplication is continuous and less than 2 is the inverse image of that half line which was open. So this is open. So this is open, etc. etc. Okay. But I wonder whether you guys know, some of you might have seen that this rational numbers Q have many other metrics. Interesting metrics called p-adic metric corresponding to any prime p. Have you seen p-adic metrics? Okay.
Yes, sir. Yes, sir. Yes.
So can somebody tell me? It will take too much time. So let me briefly describe what is p-adic metric for you. So there is actually a new kind of a norm. You choose a prime p. Then any integer, any n belonging to z, n not equal to 0, can be uniquely written as n equal to m times p to the power r, where p does not divide m and r greater than or equal to 0. Yeah. So the p-adic norm of n is defined as norm of n is equal to 1 upon p to the power r. And define norm of 0 to be equal to 0. And extend, okay. So this gives a new distance on Z, new metric. You can extend this norm to extend, so let's call this p-adic norm. Extend norm from Z to Q by defining norm of, say, A upon B, p-adic norm. Yeah, what will it be?
So norm A P by norm B P.
Okay, so this is a new norm and that gives a new metric. This metric gives emphasis to how much does P divide your number. So natural number 1 has a certain size, which is 1. P has size 1 upon P. P square has size 1 upon P square. P cube has size 1 upon P cube. And so more that P divides a natural number, closer it is to 0 in this new norm. So I must tell you that in your complex analysis course, which is going on side by side, you must be studying things like Taylor series of something. It's an expansion in Z, and it's A0 plus A1Z plus A2Z square plus blah, 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 blah. This Taylor expansion around origin in a little disk for some holomorphic function. And the greater and greater powers of Z are smaller and smaller. And so that thing converges, etc., etc. So this is a new norm on Z where divisibility by P is given great importance. And this kind of norm, as you can imagine, is very useful in studying number theory when you want to focus attention on a particular prime. So now that you know this norm, I can ask, is Q connected under this metric? So I leave that to you.
Sir,
Yeah.
I guess it will again be disconnected.
No, but you have to answer it, and I'm leaving that to you because
Sure.
these are two of our going
Okay.
tests. Now take GLNR for n greater than 0, our old example. Is it connected?
So for n
No,
equal
okay.
to 1.
Now I think Sonakshi was answering. Was that Sonakshi?
Yes, sir.
Sonakshi, why is it not connected? I want different voices. Yeah, go on.
So we can create a map from of continuous f inverse of 0 will be equals to determinant map.
So
F
there is a determinant map. Very good. Determinant is a map going from GLN or GLNR to, and determinant is non-zero always, so it goes here. Now, is this map surjective, Sonakshi?
Yes, sir. For
What?
any
Yeah.
for
So
any
tell me, why? If there is
for
some T belonging here, what is the matrix whose determinant is T?
so we can take a scalar matrix.
No, I was expecting this mistake. That's why I asked you. Okay. T11111 has determinant T. If you took the scalar matrix T, Sonakshi, what would be its determinant?
T to the power n, the
Correct.
order
So
of
you,
that matrix.
correct. So you see, you have to take T1111, and so then that has determinant T. So this map is surjective, and we saw last time that the image of anything continuous under a continuous map is connected. Sorry, image of anything connected under a continuous map is connected. A surjective continuous map from a connected space, the other one has to be connected. But you know, R star is not connected, so therefore this is not connected. Okay. How about this GLNC? Anyway, I leave it to you. I remember being asked this question when I went for my PhD entrance examination, and I gave an answer there. But I leave it to you to answer it in your own way. Okay. Now let's come to the circle. So this one is exercise. It is doable in 3 minutes in entrance interview circumstances also. Anyway, all right. The circle S1, is it connected? Bolo, a new voice this time. You think circle is connected? Yeah, you are right. What's your name? Yeah. Go on.
It is continuous image of this.
Correct, absolutely. What's your name?
Anuj.
Anuj, very good. So Anuj is saying that take the map X, or you can also call it in real terms R to S1. You can also call it T goes to cos T sin T, whatever. This is a surjection and R is connected, so this is connected. Okay, good. So this is connected. Next, let's take the n-dimensional sphere. It is defined by the equation, as you know, x1 square plus, you have to take one more of the x's. So last one will be xn plus 1 square equal to 1. And that is the n-dimensional sphere. Okay. So is this connected? So this is connected for n greater than equal to 1. What is it for n equal to 0? Yeah, Bolo?
So plus minus 1.
Plus minus 1. So this is not connected. This is disconnected. So you know your football is connected, that is the S2 and so on and so on. So this again is exercise. Let me remind you that last time we showed that any path connected space is connected. Or you may take the sphere, take any 2 points and try to pass a circle through those 2 points. Very simple. Use whatever method you want to prove that Sn is connected. Okay. Now, here's a general question. If there are 2 connected spaces, is their product connected? So you have to remember that product is never a standalone thing. A product always comes with 2 projections. These are continuous, these are surjections. So if this is connected, obviously these are connected. And how about, sorry, so this goes the other way around. So this is the answer to 10. So if x cross y is connected, then it's continuous image. How about 9? If both are connected, is this connected? So answer to 10 is yes. How about answer to 9? If x and y are connected, is x cross y connected? Yeah, somebody willing to answer?
I guess yes.
Yes, Sonakshi, you are right. And if I asked you if x and y are path connected, is x cross y path connected? What do you think? Here's a simple idea. If it is path connected and I have 2 points, let's call the 2 points as x1, y1, and the other point is x2, y2. I want to go from here to here using x is connected and y is connected. What should I do? Answer is I should introduce a new point. And that new point is going to be x2, y1, right? And now this path is a path in y. And this path is a path in x. In x, I am able to connect x1 to x2, keep the second coordinate constant. I'll have a continuous map from the interval going from here to here. And the second one will go from here to here. So it's also 2 path connected. Okay? And so is this. Both of these are true for path connected. In fact, I want to take all these exercises and change the word connected to path connected and redo the exercises. Now, here, if X and Y are connected, is the disjoint union connected? So obviously not. The picture looks like this. The disjoint union is already a disconnection. A disconnection of that will be X and Y if these are non-empty. Okay. So the only exception is, so if X not equal to empty, Y not equal to empty, then X is disconnected. Because this is the disconnection. But if X equal to empty, then X disjoint union Y is equal to Y, which is connected. Or if Y is empty, same thing happens. So this is the answer to this one. How about the other way around? If the disjoint union is connected, are X and Y connected? This you have to answer. I have been doing too much answering for you under various pseudonyms. Yes, Amit. Yeah. What are you saying? When can this be connected? Can somebody answer him? When can this be connected?
Sir, X is empty or Y is empty?
Yes. So in that situation, you can say, yeah, they are connected. But otherwise, X, so that's the only situation occurring. And so otherwise, this is not going to be connected. And so you know how to answer this question. This is a very special kind of situation. Okay, good. Very good. Now, let's come to question number 13. So I have to introduce some notation. This is my notation for the closure. Okay, this is the notation for closure. Of Y index. You know, this notation is somewhat ambiguous because it doesn't make any reference to what X is. Some people use something like closure in X of Y, whatnot. All kinds of notations are used. This is the easiest if there is no danger of any misunderstanding. So I'm asking you, if X is a space, Y is a subspace, Y is connected, then is the closure of Y connected? Yeah, any answer?
So yes.
Yes. So this is true. Proof. Sonakshi, can you rattle off a proof? Okay, suppose Y bar is disconnected, then there will exist some F from Y bar into 0, 1, which is surjective. Yeah? True? Now what? Now, since it takes both kind of thing, at points of Y, there is a point of Y bar, so there exists some x0 belonging to Y bar such that f of x0 equal to 0. And there exists some x1 belonging to Y bar such that f of x1 is 1. But then in a neighborhood of x0, because it's a discrete thing, in the whole neighborhood of x0, the value is 0. And in the whole neighborhood of x1, the value is 1. So there exists, and any neighborhood of x0 contains a point of Y because x0 is in Y bar, the closure of Y. So therefore, you can approach it via points which are in Y. So there exists y0 belonging to Y such that f of y0 equal to 0 and y1 belonging to Y, f of y1 equal to 1. And so f restricted to Y from Y to 0, 1 is surjective. And so Y will also be disconnected. So if Why did you say why? See, I gave you this very simple proof using simply maps. Okay, don't have to go back to neighborhoods too much. Is the converse of the above true? Meaning the converse will ask the following.
No, sir.
No. Okay, why not?
Sir,
Counterexample.
disjoint open ball like center at 0 and radius 1 and center at 2 and radius 1.
And so the closure contains that one extra point shared by the two, right?
Yes, sir.
You are giving a. How about what's the closure of Q in R?
R.
R, and that is connected, but Q is disconnected. Or
Yes.
what is the?
Yes, sir.
Or what's the closure of R star in R?
It's also R.
And R star is disconnected.
Yes,
Yeah.
sir.
So you see, these are much simpler examples which I already seen, but I liked your example because that shows you can think visually. That's very important to be able to think visually. Okay. Now, so the answer is no. Okay. Now we come to let Y and Z be connected subsets of X. Okay. Is, well, what did I have in mind?
Minus.
No. Because I must have done all kinds of other things earlier. I have done disjoint union here. Oh, I have done product here.
So union or intersection.
Correct, because they are subsets. So I must have this in mind. So is union connected? Is intersection connected? And if the intersection is not empty, then is the union connected? Yeah? See? What do you think? If Y and Z are connected subsets, then is union connected?
No, sir.
No, because they may be far away, but suppose they also intersect, then is the union connected? Suppose the intersection is non-empty. Y and Z are connected subsets and intersection is non-empty. Then is the union connected?
Say yes.
Yes, correct. This is Anuj answering. Whose voice is this?
So Ramveer.
Ramveer, great. Wonderful. Welcome, Ramveer. You have not answered so far, but you are giving very good answer.
But I was answering today or
You were, okay. Beginning. Very good, very good.
The irrational root 2, I was the one.
I see. Excellent. That was also a very good answer. Okay. And how about Y intersection Z connected? Is the intersection of two connected sets connected?
Yes, sir.
Yes, somebody is saying yes. Okay, I'm going to draw two connected subsets.
Sir, no.
Here is no. Okay.
Yes, sir.
That's correct. Sonakshi is right.
Sir, I'm Tithi.
You're thinking. Okay. But
Sir,
I'm drawing.
I'm Tithi, not Sonakshi.
Yeah, who is it?
Tithi, sir, Tithi.
Tithi, great. Wonderful. Whatever names you tell me you have them. I have no way of knowing. Anyway, okay, all right. So I have now shown you two sets, and one of them, okay, sorry, one of them is this one, and the other is this one. Both are connected, but their intersections, it consists of two pieces, one piece here and one piece here. This is the intersection. This dark stuff is the intersection of the yellows set and the pink set. Both are connected, but the intersection is disconnected. See? Okay. So I'm going to start the new topic, connected components now. But before I begin it, again, statutory question. My question to you is whether you have any questions to me. Okay. Any questions? 1098765432 1. Bolo.
Sir, is the counterexample for the path connectedness and connectedness question is topologist sign curve?
Oh, very good. Excellent. Very good. Somebody, yeah. So was that again Tithi? Was that your name?
No, sir, Sonakshi.
Acha. Do you have two names, Sonakshi / Tithi? Or
No,
you're
sir.
really? No. Okay. All right. That's all right. Okay. Just as I invent imaginary students who quickly give answers when I am in a hurry, anything is possible. Okay. All right. So, oh, yo, this is still very broad. Okay. Let me draw the picture. Wrong color. Okay. Let me draw the picture of this curve, which he is talking about. This is the curve, and it keeps doing very rapid oscillations as it comes close. So it's like sine 1 upon x. Take the graph of this. Take the graph of this on 0, 1. And to that, you add this vertical segment here. Okay. And take the union, regard it as a subspace. So union with 0 cross -1, 1. Okay. So take this the axis and union the graph of this. The graph of 1 upon sine x on this, union this. This is the so-called topology sine curve. Okay. It's connected but not. And to make it path, yeah, okay. Here's the topology sine curve. Now, you were saying the topology sine curve is an example of something. So what is it an example of? Yeah, Sonakshi?
So it is connected but not path connected.
It is both connected and path connected. See?
Okay.
Because I can go from here like this.
So you can take the interval, I mean, on y-axis you can take from 0 to 1, then it will not be path connected anymore.
And you don't want to join it by some path going back like this, yeah? Then it won't be path connected. But is it connected?
Yeah, then it will still be connected.
Correct, that is right. So I don't know which one of them is called topology sine curve. Perhaps Sonakshi is right, and the topology sine curve does not include this little extra piece which connects it. In that case, indeed, this thing is connected but not path connected. Good. So this also shows that you have been reading literature. That is very good because one doesn't invent such names on the spot. So you might be able to invent such examples. So very good. Please keep. Yeah.
Sir, actually, you take any space with more than 1 point, and if we give it the trivial topology, it is connected but not path connected.
Yes, take a discrete space consisting of 2 points. Yeah. And it's connected but not path connected. But those examples are kind of pathological, you may say. You want to have your spaces as the kind of spaces you see around you, the spaces which an engineer, scientist, etc., will find useful and which appeal to your visual sense. So in topology, we basically focus on such spaces which are nice and not pathological. Okay, now, so let's begin the new topic, connected component, and the definition is this. If I have topological space, a connected component of that X is a subspace Y such that Y should be non-empty, otherwise I am not going to call it connected component. Y should be connected, and if, so here I need to show something by my pen. If Y subset of Z subset of X is such that Z is also connected, then Y should be equal to Z, meaning there is nothing larger which is connected. So this is a maximal connected subspace. There may be several such, each one of them is a connected component provided they are non-empty. So now let's ask for connected components of the following spaces. What are the connected components of R?
It's only one component over.
Yes, and that is R itself. What are the connected components of R star?
Two components, positive and negative real numbers.
Correct. So here the answer is R, here the answer is R plus, R minus. What are connected components of Q?
The singletons.
Every point, every singleton point.
Yes.
Okay. Now, what are the connected components of empty? What are connected components of the empty space?
Empty set itself
No,
So
because the
nothing
connected component has to be
would be
non-empty.
non-empty.
So it has no connected components, has no connected components. Okay. All right. So the set of connected components is empty. All right. So you have understood the notion of connected components, and in Q I accepted your answer that singleton is the only connected non-empty subset, but you didn't justify it, so you'll have to justify it. So justify it in your mind and it's something that all of you have to do for yourself. See, mathematics is not a spectator sport, it's a participatory sport. Okay, so you all have to do these things yourself. Now, going back to this exercise, let Y be a connected component of space X. Show that Y is closed in X. Why is Y closed in X? Why is the connected component closed? Yes, Vijay, what are you saying? Oh, Vijay, yeah, as okay.
Sir, because
yes, somebody answering. Yeah, go on.
sir, because we know that if Y is connected, then its closure is also connected. But
Correct.
Y is a subset of Y subset of Y closure, and Y is the maximal connected.
Correct. So Y
So
equal to Y
Y
closure,
equals to Y closure.
and now one more thing you have to say that the closure is indeed closed. No, you have to prove that, you define closure to consist of all limit points, all points of Y and limit points of Y, but you have to show such a thing is closed. Okay, good. So because of this, a connected component is closed. And is a connected component open in X? Yeah, what's the answer? Is it open? Here's where your pictorial intuition may mislead you, because in the nice kind of spaces which you can imagine, it is also open. But you take Q in R, what are connected components? Single points, are they open? No, they are not. So here you think about here you think of X equal to Q and Y equal to point. So it's a connected component of Q. Every point is a connected component of which point? It has to be some particular point. So there's one number which is a great favorite in mathematics among all rational numbers. This one, I remember being introduced to this rational number in my 5th or 6th standard, and it was given the name pi, and it had magical properties. And later on, they removed the magical properties. I also remember being taught that Pluto was a planet in school, and then they told us that Pluto is not a planet, and so on, so on. But there's still Pluto there. There's still that piece of rock going round and round. Similarly, this rational number is still there, though it may have lost its importance. But anyway, it's good enough for this example. So y equal to, and like our undergraduate teachers emphasized, you have to put a curly bracket when I want this to be a subset. Okay, all right, great. So this is not open now. So the space Q, the topological space Q, this one, inspires this definition. The space is called totally disconnected if it has no non-empty connected subsets. Eh? What did I say? This is utter nonsense. If, okay, so let me correct this.
So I guess you wanted to say singletons.
Yes, yes, it has no non-empty connected subsets other than single point. Oh, now back to this. So question, is the empty space totally disconnected?
So yes.
Yes. And is it connected?
So yes.
Yes. So it's both connected and totally disconnected, right? Yes.
Yes.
Yeah.
Yes.
What other spaces are like this, both connected and totally disconnected?
So singleton.
Correct. Those are only ones, empty and singleton, nothing else. Okay, all right. Now, question. What is any connected component of totally disconnected space? So singleton, because there are no,
Singleton.
correct, obviously so the way it is defined. So exercise show Q with usual topology is totally disconnected. What about Q with p-adic topology? You are supposed to answer it at your leisure somewhere. Okay. Now the next exercise is the Cantor set is totally disconnected. Everybody knows what's the Cantor set, right? It's the favorite of analysis textbooks, major theory, all kinds of things. So the Cantor set is totally disconnected. Do you remember what's the Cantor set?
Yes, sir.
Yes, sir.
You begin with the interval, any interval, and you remove the 1/3 in the middle. Then of the remaining portions, which are now the 2/3 closed, two closed intervals, again remove the middle 1/3 and keep removing, keep removing, keep removing. So take all those removed things, take their union and remove the union, or take the intersection of what remains, whichever way, and that is the Cantor set. And that is totally disconnected. You see, it's already working because given any point and any other point, soon some little interval is going to come in between and that's going to be removed. So these two are going to fall in two different components. So no 2 points are ever going to land up in the same component. So finally the connected components are going to remain singleton. It's pictorially obvious. Writing the proof, you will have to set up appropriate notation and do it. Okay, so again we are to the point where I have to ask you whether there are any questions. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, boom. Okay, so there are no questions. Very good. That shows what a clear teacher I am. Good for me. Now, so let's again come to definitions. A topological space is said to be locally connected if given any point, and now I have to write some notation by hand clearly. Then any point x belonging to x, there is an open subset with x is in x and u is in x, and there and given any such, there is a connected open set x with x belongs to x. This is inside u. So this is saying that there is a basis of open sets which consist of connected sets, because such sets are going to form basis. Inside any U, there is such a V containing of for a given point. So U is the union of such V's, because take any point X of U and then there's a V around it. So there's a basis. So so this alternative way of saying it. A basis for the topology of X consisting of connected open sets. So such a space is called locally connected, you see. So your topology sine curve, it's not locally connected because it's going like this. And the other piece was this vertical line. Okay. And even if I connect it. So let me connect it so that it will even be path connected. This is path connected, but it's not locally connected because if I take this neighborhood, so let me show the neighborhood by highlighting it. If I take this neighborhood, okay, of this here, violet point here, the point, or now it looks violet, but this point. Okay, I'm going to take a point here. I take this point, and if I take any neighborhood of it, it's not connected. Because again and again, this is crisscrossing going out. Plenty of independent segments are crossing it. So it has infinitely many connected components. But it is, the overall space is connected, but it's not locally connected. Overall space is connected, it's even path connected. You can go like this. To go from here to a nearby point there, you will have to go travel like this and do all the zigzag till you come there. Now, is R locally connected? Yes or no?
Yes.
Yes. Can a totally disconnected space also be locally connected?
Yes, sir.
Yes, sir.
For example,
R with discrete topology.
yes, any discrete, why R? Any discrete space is totally disconnected, but also locally connected. Also, empty is totally disconnected, locally connected. Now, if X is locally connected, show that any subspace of X is again locally connected. Is it true? Is this true? So I should remove this show. This show that looks like I am telling you it is true. Okay, so to delete it. What's the answer? A locally connected topological space is any subspace again locally connected. True or false? Yeah. Yes, thank you. It is false.
R
Yeah.
and Q.
Yes, R and Q. That's an example. Now, if X and Y are locally connected, how about the product? See, we go through all these, boring things one after the other because with every new property, you have to check on these things. So I'm not going through the list of these questions. You should know now how to ask all these basic questions yourself. Given every property you want to check that, oh, is this property inherited by subspaces? Is it inherited by quotients? Is it inherited by products? Is it inherited by disjoint unions? And what are questions you know about what happens to the property with respect to those? You have to play with those properties only and play with examples and counterexamples. Then that is called exercise. It's like what the athletes do, okay, and what players do. A cricketer who also does push-ups, pull-ups, and all such things. And on the field, he's not going to do push-ups or pull-ups, but in preparation for hitting a century, he does push-ups and pull-ups, among other things. So think of all such exercises as standard push-ups and pull-ups, which you have to do for your mathematical muscles, which means your brain. And then when you do interesting things, all this is going to give you ease of doing whatever you want. Okay. Now, so I cannot sustain my interest in statement after statement of this kind, because where do these come from? Because in the afternoon, I sat down and typed this, and then I thought of what should be interesting questions. So I made up all these questions then, okay? And so I cannot get enthusiastic about it once again after 1 hour. In fact, my regular students tell me that I should not prepare my lectures because they are more interesting when I don't prepare them. And if I prepared them, then in the delivery I get bored and then it's not that interesting. Okay, all right. Now, if X is locally connected and if F from X to Y is continuous surjective, is Y locally connected? Okay. If F X to Y is a continuous map that is surjective and open and X is locally connected, then Y is locally connected. This is true. Prove it. Okay, so that brings us to the end of today's lecture, and there are 4 minutes left. And so I can once again ask you any questions.